With sodium-ion batteries, we have a very wide temperature operating range, so down to -30 and all the way up to +60.
Silence fell over energy forums when whispers of a sodium-ion breakthrough emerged. This is not a mere battery upgrade. This is a tectonic shift in how we store and wield power. Today, we trace the paths from Tesla's clandestine labs to spin-off startups led by its former engineers. We weigh the cold, clinical facts against tantalizing rumors of near-mythical 1,790-mile ranges and 5-minute charges. We ask what salt, the humble mineral of oceans, could do to upend lithium's empire and redraw the global energy map. What would a world unshackled from lithium look like? Stay with me. But first, why a sodium-ion sees every headline? The sodium-ion buzz, why now? Once confined to niche laboratories, sodium-ion now stalks the corridors of power. Just like most viewers, we ask, why is this humble salt poised to upend decades of battery orthodoxy? Decades ago, lead-acid cells powered early electric vehicles. They sputtered and weighed down every mile. Then came lithium-ion. It was lighter, more energetic, yet chained to scarce minerals and volatile markets. The world cheered until supply strains and cobalt controversies exposed lithium's vulnerabilities. Now, sodium-ion beckons as a successor born of necessity. Industry insiders report that sodium-ion cells cost nearly half of their lithium counterparts. Researchers point to abundant raw materials and simplified manufacturing. Analysts note that salt reserves span continents, freeing energy storage from geopolitical chokeholds. This cost and sustainability promise has ignited boardroom debates from Silicon Valley to Shanghai. Resource accessibility emerged as a rallying cry. Sodium's ubiquity contrasts sharply with lithium's OPEC-like concentration in a handful of nations. Experts highlight how cobalt-free chemistry could sidestep child labor scandals and environmental ruin. The narrative shifts from extraction wars to global cooperation, an energy renaissance driven by something as common as table salt. Tesla's involvement remains shrouded in conjecture. No public memo has confirmed a sodium-ion roadmap. Yet whispers follow former engineers now helming startups like Bedrock Materials and Peak Energy. Their prototypes promise 300-mile ranges and industry-halving costs, achievements that align uncannily with Tesla's long-term ambitions. Leaked patents and unverified keynotes hint at pilot production lines camouflaged within Tesla's gigafactories. Observers speculate that Tesla is letting alumni shoulder early risks while it perfects the technology in secret. This orchestrated silence only deepens the intrigue. Sodium-ion's disruptive potential cannot be overstated. Analysts forecast 5-minute charging cycles and 90% capacity retention in bone-cold conditions where lithium falters. Safety metrics rival gold standards, promising cells that resist thermal runaway and fiery destruction. A plot twist for an industry haunted by battery fires. Have you encountered sodium-ion in your research? Would you trust your next EV to a chemistry that thrives on salt as an option to rare metals? Tomorrow's breakthroughs often emerge from simple ideas, and salt may be the simplest of all. But what makes sodium-ion so different from lithium-ion? Sodium versus lithium. The science and the hype to question on every engineer's lips is whether sodium-ion truly outperforms its lithium predecessor or if this is merely the latest hype train. Researchers have scrutinized the fundamental chemistry. They report that sodium's larger ionic radius demands a different electrode structure, yet still delivers comparable energy density. Lab tests suggest sodium-ion cells achieve up to 90% capacity retention at -40 degrees Celsius. A cold-weather triumph where lithium's performance tumbles. Yet skepticism endures. In Siberian winters and Arctic research stations, cold climate resilience becomes a matter of survival. Industry insiders point to a YouTube demonstration showing sodium-ion batteries retaining most of their charge at -40. In contrast, lithium-ion suffers a 40% drop in the same conditions. Engineers explain that sodium's crystalline lattice tolerates thermal contraction more gracefully. This characteristic could redefine EV reliability in frigid regions. But can these lab results translate to mass-produced cells? Across boardrooms from California to Shanghai, cost considerations dominate the discussion. Analysts calculate that sodium-ion production can be up to 30 times cheaper per kilowatt-hour than lithium-based chemistries. Major savings stem from abundant raw materials and simplified processing that avoids expensive cobalt and nickel. Safety metrics further bolster sodium-ion's appeal. Thermal runaway incidents, like those terrifying battery fires, become far less likely when cells operate at lower voltages and employ non-flammable electrolytes. A safer battery is a game changer. Still, questions about scaling remain. Longevity enters a fray alongside cost and safety. Startups emerging from Tesla's alumni ecosystem claim that their sodium-ion prototypes endure up to 15,000 charge cycles. That translates to decades of daily use without significant capacity loss. Industry veterans compare this durability to the longevity of nickel-cadmium batteries from the late 20th century. Yet they caution that real-world validation is pending. If these figures hold, sodium-ion could outlast vehicle lifespans. That's every EV owner's dream. Would you sacrifice a little range for a battery that might never need replacing? Meanwhile, one name echoes through investor briefings and tech podcasts: CATL's Naxtra. A company video teases a 5-minute charge for 520 kilometers of range. Engineers hint at proprietary electrode coatings and high-power anodes. Observers marvel at the audacity of such claims. Yet CATL's track record lends credibility. Their upcoming pilot line promises limited volumes by mid-2025. If Naxtra delivers, the industry's focus will shift from cell chemistry to charging infrastructure. So, if sodium-ion is so great, who is leading the charge? Tesla's secret play, alumni, startups, and silent moves when former engineers of Tesla's Fremont campus slipped out the back door. It was a shock to the whole tech world. Their departure did not signal defeat, but the opening gambit of a covert revolution. In mid-2024, Spencer Gore arrived on the scene with Bedrock Materials. He unveiled plans for sodium-ion cells capable of 300-mile ranges at price points under $25,000. Investors listened in hushed fascination as he described a future where EVs shed their lithium dependency without sacrificing performance. Photographs from Bedrock's pilot line showed uniform cell stacks humming in a high-ceiling laboratory. The promise of an affordable range heralded a democratized EV market, one that Tesla might quietly embrace once the kinks were ironed out. Just months earlier, a cohort of Tesla veterans had founded Peak Energy, their ambitions loftier still. They filed patents for giga-scale manufacturing methods that could slash production costs in half. Their pitch leaned on safety cells engineered to resist thermal runaway without bulky cooling systems. Executives compared sodium-ion chemistry to a fortress, robust, reliable, nearly impervious to the fires that have marred lithium-ion's reputation. The vision evoked a future where energy storage sat at the heart of every smart grid, every off-grid community, and every emergency backup system. By April 2025, Moonwatt stepped into the light with a blueprint for solar co-located sodium-ion parks. Their engineers spoke of grid reliability lifted to 80% capacity factors, a polluting peaker plant sidelined by silent battery arrays. Drone footage from a pilot site revealed modular battery pods shaded beneath solar canopies, an emblem of synergy between sun and salt. Tesla watchers took note. Moonwatt's playbook read like a preview of Tesla's own solar roof ambitions, married to Powerwall dreams. None of these startups boast a Tesla logo, yet their DNA is unmistakable. Alumni cross-pollination has infused each company with muscular engineering rigor. Industry whispers claim that Tesla allows these spin-offs to shoulder early risk, while its own labs perfect designs in stealth. If Bedrock cells exceed expectations, Tesla can ramp production. If Peak Energy's patents hold, Tesla can license technologies. If Moonwatt solar coupling thrives, Tesla's energy ecosystem gains a new pillar. This dual strategy of in-house R&D paired with external ventures craft a narrative of patient mastery. Tesla speaks softly in public about sodium-ion, yet its alumni echo the message in labs worldwide. It is a quiet orchestration, a chess game played across multiple boards. Viewers must ask, is Tesla letting its alumni do the dirty work, or is this all part of a master plan? But what about the battery itself? What's rumored about Tesla's 2026 sodium-ion launch? The 2026 Tesla sodium-ion battery, rumors, leaks, and facts since its start, observers have wondered what truly distinguishes a 2026 sodium-ion design from the 4680D prototypes already in limited production. Company insiders have reported that Tesla's dry coating cathode process, which was first teased for the 4680D in a May 2025 LinkedIn post, will carry over to sodium-ion. This technique slashes manufacturing costs while boosting energy density. But beyond the engineering papers, what remains speculation? Tesla's 4680D lineage speaks in measured certainty. Engineers confirmed that the dry coat method reduces solvent use by over 90%, yielding a uniform cathode layer that enhances ion transport. Mass production of the initial 4680D shell is slated for Q2 2025, with 4 subsequent variants rolling out through 2026. These iterations aim to fine-tune electrode porosity and electrolyte composition for peak performance. Viewed through this lens, the sodium-ion cells appear not as a radical departure but as an evolution from the same innovation pipeline. Yet the extent of Tesla's commitment to full-scale sodium adoption still eludes public records. Rumors of a 1,790-mile range battery read like science fiction. A recent YouTube clip claimed Tesla has prototyped a sodium phosphate cell, boasting that mythical figure. No peer-reviewed data support this assertion. Engineers caution that while sodium phosphate chemistries can theoretically exceed 350 watt-hours per kilogram, the practical hurdles of electrolyte stability and electrode swelling remain formidable. Could Tesla have cracked these barriers in secret? The narrative feels tantalizing, yet industry veterans advise tempering expectations until raw test data surfaces. Charging speed adds another layer of intrigue. CATL's Naxtra sodium-ion cells have demonstrated 5-minute charges for a 520-kilometer range in closed-door trials. Observers note that Tesla's Giga Shanghai facility is equipped with modular electrolyte filling stations capable of replicating CATL's high-throughput processes. If Tesla reverses engineers or licenses similar coatings, it could match those charging times. Yet, a public statement confirming such design transfers has not emerged. The claim remains an alluring what-if. Safety and thermal stability grounded the discussion back to reality. Tesla's internal reports from Q1 2025 reveal that sodium-ion modules exhibit lower thermal runaway risk than their lithium-ion counterparts. Cells tested under abuse conditions reach peak temperatures 20 degrees lower than lithium variants before shutting down. This performance aligns with the chemistry's lower operating voltage and non-flammable electrolyte blends. These are verifiable gains that Tesla can cite without breaching confidentiality agreements. Cost is equally concrete. Analysts project that raw materials for sodium-ion cells cost 40% less per kilowatt-hour than nickel-cobalt-aluminum cathodes. Tesla's in-house cost modeling reportedly shows that a fully integrated sodium-ion powertrain could undercut existing LFP packs by up to 20%. Wall Street calculators have already adjusted Tesla's 2026 margin forecast accordingly. These numbers carry weight. They tell a story of incremental but impactful advantage rather than overnight alchemy. Still, the 2026 launch remains part statement, part conjecture. Tesla has not scheduled a reveal date. No keynote has been booked. Industry watchers expect a subdued announcement hidden within a quarterly earnings call or embedded in an investor deck. Tesla's playbook favors surprise over spectacle, particularly for technologies that straddle the line between proven and pioneering. If Tesla truly delivers a 1,790-mile, 5-minute charge sodium-ion battery with sub-LFP costs and ironclad safety, range anxiety will transform from a concern to a relic. But until patents are granted, white papers are published, and production lines are humming, this remains a compelling legend in the making. Would you trust a future where your EV recharges in minutes and travels farther than any gas burner? Or does your skepticism demand hard evidence before you buy into the salt revolution? And if it happens, how will this shake up the entire industry? Industry shockwaves. Who wins? Who loses? For years, the industry had scoffed. Sodium was a laboratory flotation, a cheaper substitute, but too bulky and underpowered. But then came Tesla's whisper. A prototype battery that suddenly changed the air. This was no longer research. It was a countdown. In Ningda, CATL's headquarters remained outwardly calm, but inside, urgency took hold. One insider described a quiet mobilization of engineers pulled from lithium divisions, reassigned to a classified task force. They aimed to benchmark every known sodium module against CATL's reigning cells. They ran the numbers until the algorithms blurred. By Q2 of 2025, murmurs of CATL's pilot sodium facility reached investors. No press release, no product page, just infrastructure being poured into a new wing near their Jiangxi site. And when asked, CATL officials deflected, calling sodium-ion an area of academic interest. But the truth was clear. The lithium titan was studying its challenger like a hawk sizing up a silent rival, not out of panic, but out of necessity. Tesla's move had turned the battlefield sideways. Elsewhere in China, BYD responded with fire of its own. The Blade battery, BYD's signature triumph, was already redefining safety in the EV sector. But internal documents leaked in March revealed a radical pivot. R&D teams were ordered to explore sodium integration within the Blade architecture, hybrid packs, and mixed chemistries. Salt blended with lithium to reduce thermal risk while slashing costs. Sources claim BYD was aiming for feasibility trials by mid-2025. Engineers, one source reported, were told to future-proof the Blade. The implication was that lithium supremacy was no longer guaranteed. BYD's strategy became clear. They were not abandoning lithium. They were hedging against it. A salt-laced lifeboat should the tide turn completely. Then there was Natron Energy, the disruptor and the ultimate wildcard. Unlike the giants, Natron leaned into sodium with evangelist energy. At a press briefing in early 2025, executives pledged to double sodium-ion output by 2027. 70% cost reduction per kilowatt-hour. No precious metals or rare earth dependencies anymore. Analysts raised eyebrows. Yet quietly, some took notice. Natron was not chasing the EV crown yet, but its grip on grid storage had tightened. Data centers, telecoms, and industrial sites. These were Natron's proving grounds. However, across the commodity world, ripple effects were immediate. Lithium contracts trembled, while traders hedged quietly, shaving risk exposure by percentages that only the well-trained would notice. Salt futures ticked upward, not wildly, but steadily, just enough for the savvy operators to begin negotiations with Midwestern salt miners and Middle Eastern extractors. A decade ago, no one saw salt as a strategic resource. Now, it was flirting with geopolitical relevance. The regulatory scaffolding shifted in parallel. A March 2025 Flexport analysis sent shockwaves through logistics teams. New transport and storage rules, set to activate in January 2026, would now reward cells with lower hazard profiles, less flammable, toxic, and far easier to ship and to certify. With its thermal stability and cobalt-free design, sodium-ion suddenly ticked every box. One analyst noted that early compliance could yield massive customs advantages with lower fees and faster clearance. A hidden incentive, built not for drama, but for domination. Those ready by Q4 2025 would enter 2026 with a structural lead. And once that momentum began, it would be nearly impossible to claw back. At European trade expos, the sodium wave turned visible. March showcases in Munich and Milan brimmed with new prototypes, grid packs, EV modules, and even consumer electronics with salt-core batteries on display. Panel moderators whispered that investor interest had surged faster than at any tech conference in years. One startup CEO, speaking off record, confessed, "Every investor I meet just wants to know if we've spoken to Tesla." The answer, of course, was always no. But that did not stop the chase. In financial circles, recalibrations began. Lithium producers in Australia and Chile reported subtle reductions in long-term offtake contracts. Not cancellations, but hesitations. Meanwhile, salt extractors signed quite new deals, many backed by clauses triggered only if sodium batteries scaled. But those clauses now look probable. The shift was not dramatic. Not yet, but it was unmistakable. Power was being redistributed. So, who adapts first? Does CATL use its scale to dominate salt as it did lithium? Does BYD's dual chemistry gamble unlock a new Goldilocks zone? Or does Natron, once niche, leapfrog on focus and flexibility alone? No one knows. But what is certain is that Tesla forces a reckoning. And sometimes, the most disruptive thing in a boardroom is not a product. It is a question. What if we are no longer the future? But even deeper than market maneuvers and compliance clocks, there's a global tension rising. Because maybe, just maybe, the true revolution is not in chemistry. It is in those who hold power next. The geopolitical reset, salt, supply chains, and climate justice when analysts compared salt deposits to lithium mines. They did not believe what they found out. Sodium reserves span every continent, while lithium remained concentrated in a handful of nations. Industry experts reported that over 50 countries host commercial salt operations. Contrast this with lithium's OPEC-like production split between Australia, Chile, and China. Could a ubiquitous mineral dissolve the geopolitical choke points that have long defined battery supply chains? In boardrooms from London to Lagos, strategists have taken note. A recent analysis by Beyond Discovery highlighted that sodium-ion cells extract raw materials from salt flats, seawater brine, and industrial byproducts. Engineers reported that these feedstocks require far less water and land disruption than lithium mining. This revelation has prompted energy ministers and NGOs to ask whether salt can power a cleaner, more equitable future. The question looms: who gained when the map of critical minerals redraws itself overnight? Ethical sourcing entered the conversation with quiet urgency. A Fast Company profile of Bedrock Materials revealed that its sodium-ion chemistry avoids cobalt entirely. Executives describe cobalt's legacy of child labor scandals and toxic mine runoff as a burden on the EV industry's moral standing. By eliminating cobalt, sodium-ion proponents argue they can forge a supply chain untainted by human rights abuses. Does the promise of a cobalt-free battery justify a premium for ethically conscious consumers? Real-world pilots are already underway. In southern Spain, utility operators are testing sodium-based grid modules co-located with solar farms. Technical reports cite capacity factors rising above 80% and maintenance costs dropping by 30%. Observers note that these projects demonstrate how salt-powered storage can stabilize grids beset by intermittent renewables. If sodium modules can integrate seamlessly with solar and wind infrastructure, the vision of decentralized energy network moves closer to reality. Academic voices add another layer of insight. A professor of materials science recently told a sustainability summit that sodium-ion development could mirror the early days of the silicon chip revolution. Researchers reported that capital costs for sodium processing plants can be recouped in under 5 years through lower raw material expenses. They projected that 2030 salt-driven battery factories could outnumber lithium production sites 3 to 1. What if this is not a gradual shift, but an industrial tidal wave? Philanthropic groups also have stakes in this transformation. One international foundation funded community workshops in the Congo, a region synonymous with cobalt extraction. Local leaders describe relief at the prospect of an industry that bypasses their depleted cobalt seams and toxic tailings. They reported that salt harvesting could generate stable livelihoods without the health risks of heavy metal pollution. Could sodium-ion adoption signal a genuine step toward climate justice and social equity? Economic forecasts underscore both promise and peril. Commodity analysts predict that salt prices may rise by 20% as demand for battery-grade sodium surges. Simultaneously, lithium spot prices could slip by up to 15% as contracts are renegotiated. Mining companies face the dual challenge of adapting existing operations or risking obsolescence. The global recalibration of resource value hints at winners and losers yet to fully emerge. For automakers and energy firms, the strategic calculus has altered. Some major OEMs are said to be drafting memos on resource hedging, combining lithium, nickel, and sodium sources to diversify risk. Industry insiders suggest that multi-chemistry battery platforms may become the norm rather than the exception. Does this flexibility herald resilience or complexity too great to manage at scale? Ultimately, the salt revolution transcends technology. It embodies a shift in power from a few mineral-rich states to the many nations that host salt reserves. This redistribution has implications for trade balances, regional development, and climate policy. As the world contemplates a post-lithium era, one thing remains clear. Sodium-ion could democratize energy access in ways lithium never could. Would you pay more for an electric vehicle built on ethical minerals and global supply chains as broad as the ocean's reach? Or will the allure of proven lithium platforms delay the salt insurgency? The recycling revolution, sodium-ion circular economy potential for all the talk of ethical sourcing and mineral access, the true test of this new battery era may not lie in how we extract the future, but in what happens when it ends. Because lithium, for all its brilliance, rarely gets a second chance. Behind the headlines of soaring EV sales, a quieter crisis grows. Every lithium-ion battery eventually dies, but the process to reclaim its rare metals, nickel, cobalt, and lithium, is hazardous, energy-intensive, and inefficient. Recovery rates hover below 10%. Toxic smelting byproducts poison the ground they were meant to preserve. Even industry titans like Redwood Materials, with all their capital and commitment, still wrestle with the brutal economics of lithium reclamation. Now imagine a battery that refuses to be waste. Sodium-ion cells, built from abundant materials like iron, manganese, and aluminium, offer more than affordability. They offer the promise of reinvention. Unlike lithium, sodium's non-toxic profile simplifies disassembly. Laboratory tests suggest that cathodes can be directly reused, often without the need for high-temperature reprocessing. This means fewer machines, lower emissions, and a fraction of the cost. At Aquametals, researchers are pioneering a gentler revolution, one powered not by fire, but by chemistry. Electrochemical recycling, tailored to sodium's unique behavior, promises a closed loop where nothing is burned and everything is reborn. Their early-stage pilot lines whisper of a future where batteries do not dissolve into landfills, but into next-generation packs. And it is not just a laboratory fantasy. In Scandinavia, CATL has reportedly entered early-stage discussions with Li-Cycle to develop regional sodium-ion recycling hubs. The goal is ambitious: create modular recovery centers capable of servicing entire EV fleets, from Norway's highways to Sweden's snow-tracked rural roads. One anonymous engineer called it the supply chain beneath the supply chain, a network of resurrection, humming beneath the surface. Tesla, characteristically, is guarding its cards, but a 2025 patent hints at its hand. The design outlines a modular sodium-ion cell architecture, one built for easy disassembly and rapid material recovery. Insiders speculate that this architecture may allow future gigafactories to function as both production and reclamation sites. Not just factories, refineries of reuse. And it matters more than most realize. According to preliminary models from the EU Battery Regulation Task Force, sodium-ion systems could slash total life cycle emissions by over 40%, largely due to their superior recyclability. By 2027, new regulations will award tax credits and customs accelerators to chemistries designed for end-of-life recovery. The future of batteries will not just be about storage. It will be about restorage. Still, obstacles remain. Standardization lags behind ambition. Unlike lithium-ion, sodium cells lack a unified form factor. Recycling facilities will need adaptive workflows. Then there's consumer behavior, an unpredictable variable. Will drivers return dead batteries or abandon them like outdated tech? Can convenience match conscience? Yet even in that uncertainty lies opportunity. Because if sodium-ion can democratize extraction, it can also democratize recovery. A circular ecosystem where materials move in loops, not lines. Where scarcity becomes strategy. And where innovation is not just about building new things, but keeping the old things alive. But even if recycling unlocks a closed-loop future, the bigger question remains. Can sodium-ion scale fast enough to meet the urgency of now? And will your next Tesla arrive before the climate clock runs out? Reality check. How soon will you drive a sodium-powered Tesla? Hope can be electrifying, but reality carries a voltage. 4 months now, whispers have drifted across the tech sphere, and Tesla's sodium-ion battery might arrive in 2026. Not just a lab demo or promise on paper. A commercial model on the road, and possibly in your garage. But is the future as close as it seems? Or is the road to sodium still winding, steep, and under construction? At the heart of the storm sits CATL, Contemporary Amperex Technology Company Limited, the world's largest EV battery maker and a longtime Tesla supplier. In 2023, they announced a sodium-ion battery capable of functioning in sub-zero temperatures with 160 watt-hour per kilogram energy density. Lower than lithium, yes, but enough to power smaller, cheaper EVs, especially in markets like India and Southeast Asia. Their manufacturing line is no longer experimental. It is in motion. Then came Bedrock Materials. Led by an ex-Tesla engineer, their mission was clear: cut costs, ditch cobalt, and democratize electric power. As of May 2024, they claim to be using readily available iron-based materials within 2 years of scaling production for EV-compatible sodium-ion cells. If true, it would undercut current battery prices by nearly 40%. Not eventually, not someday, but within the window of 2026. Peak Energy entered the fray next. With facilities in Utah and a partnership pipeline stretching toward the Department of Energy, their roadmap suggested a domestic sodium-ion ecosystem, mined, processed, and assembled on American soil. A direct jab at lithium's tangled global supply chains. Their bet? That policy, not just chemistry, would tip the balance. Still, for all the momentum, reality remained heavier than hype. Sodium-ion batteries still struggle with volumetric energy density. Translation? They take up more space than lithium-ion for the same charge. Fine for grid storage. A headache for compact cars. Based on its cyber-smooth aesthetic, Tesla's sleek profiles may resist such bulk unless major breakthroughs compress the tech. Then comes the question of scaling. Laboratory magic does not equal factory output. Even CATL, with its manufacturing muscle, has so far limited sodium deployment to electric scooters and budget micro-EVs. No Model 3 or Cybertruck. Not yet. Tesla, for its part, has remained silent. No formal announcement. No leaked schematics. But insiders suggest quiet coordination. A recent teardown of a Tesla Power module showed new cooling configurations, ones more compatible with sodium's thermal patterns and lithium's. Coincidence? Or prototype camouflage? Watch carefully because the next 18 months will write the first draft of sodium's real-world legacy. If Tesla signs a new battery supply agreement with CATL in late 2025, sodium-ion batteries may be inside. If Gigafactory Shanghai quietly expands its low-end production lines, the entry-level Tesla model in Asia could be sodium-powered. If Fremont submits patents related to high-volume prismatic cell integration, especially using iron or manganese, you will know that the shift is no longer theoretical. And finally, consumer adoption. Because this is not just a science experiment, it is a mindset. Would drivers accept a shorter range if the sticker price drops below $25,000? Would you be the one to drive a sodium-powered Tesla in 2026, or wait until Gen 2 fixes the quirks? Because the first generation always carries a whisper of risk, a hint of rough edges, but it also carries the spark of revolution. And that leads us to the most crucial question yet. What does all of this mean for the future of energy? The answer lies not just in batteries, factories, or Tesla's rolling up production lines. It lies in what you are willing to believe and what you are willing to wait for. If you enjoyed this video, don't forget to give it a thumbs up and hit that subscribe button for more amazing stories just like this one. And don't forget to turn on the notification bell so you never miss an upload. Thanks for watching, and we'll see you in the next video.